welcome to the lecture on properties of heat affected zone. So, we have already seen that when we do the welding, in case of fusion welding, we come across the various zones, and we have the weld metal zone, you have heat affected zone, and then you have the unaffected base metal. So, as we know that since this heat affected zone is subjected to the heating and cooling. So, there is microstructural changes in that zone, and that affects the properties of that zone, and that ultimately will be affecting the properties of the welded joint. So, we must know that what way the properties, especially the strength, toughness and related things are affected, and that too especially in the heat affected zone, because as you see that after the fusion boundary zone, you have a zone where there will be the grain growth which is occurring, and then you have recrystallization, then you have further grain refinement. So, and then you have intercritical zones further. So, so we will be talking about what will be the properties of those heat affected zones, especially with regard to the strength and toughness properties, how they are affected in the heat affected zone. So, the prediction of the properties of grain growth zone is required to know the amount and extent of grain growth and weld thermal cycle, because properties very much will be depending upon the change in the grain shape and size. So, as we know that grain growth is very much associated when the material is heated during the welding, it is heated to a higher temperature, and then further it is cooled. So, that there will be grain growth zone, and that grain growth zone prediction itself is important, because from there only we will be able to predict its properties. So, knowing the weld thermal cycle, under what thermal conditions the specimen is subjected to, we have to know that how much will be the order of the grain growth, that is extent of grain growth, and then what will be its effect on the temperature. So, what happens that normally if you talk about the heat affected zone. So, in the heat affected zone mostly you will have the increase in the strength in that region, but at some of the occasions we also see that there will be even the decline in the strength also in the heat affected zone. So, there may be softening also, that is also observed because it is heated to temperature around A1. So, that may be subjected to excessive tempering. So, that may lead to even the softening also. Now, that also depends that what is the specific heat input of the welding process. So, depending upon the specific heat input of the welding process also, you will have the extent of these tempered zone formation. So, that can be predicted. So, when you suppose for example, when you do the welding of the large thick plates or large thickness steels using the electroslag welding suppose. So, in those basically what happens, these zones of these tempered zones or the softened zone, they may shift towards the temperature even A3. So, that also or even slightly above A3 in that zone also it may be shifted. So, normally what happens that if you talk about the hardness values in the case of these HAZ region. So, normally you may have two types of steels, and you may have a steel which is having less carbon, or in some case it is having somewhat higher. So, what happens that if suppose if you just take the example that if suppose you have a perlitic free steel, and if you compare that with the low carbon steel. So, if you have a perlitic free steel where the carbon is less than or equal to 0.09%. So, they hardly react to these thermal cycles, whereas the steels in normal case like the low carbon steels, they are very much sensitive to this thermal cycle. So, so if you take the for the low carbon steel, and if you try to see that how they how there will be change in the hardness of these two specimen. So, the graph shows, so if you look at the graph, so suppose you have if you look at a low carbon steel, in that case you will have normally they are very much sensitive. So, suppose you have this zone is the weld zone, and then you have another zone is the HAZ zone, and then you have the base metal zone. And if suppose this is your hardness, so if the hardness is on the abscissa ordinate, and your if you take the distance along the length, so you will have the weld metal zone, then you have HAZ, and then later on your base metal comes. So, if you talk about the perlitic free steels where the carbon is very very in that case your this is how the variation goes. So, this is for the perlitic free steels. And similarly, if you try to see for the low carbon steel, so in those cases this is a conventional low carbon steel. So, in those cases what happens that the hardness is much smaller in this case, but in the HAZ zone it increases a lot, and then further it will come down. So, and then so this way it will be varying. So, this will be for the conventional low carbon steel. So, such is this is hardness can be of any scale, maybe Vickers hardness or so. So, you will have about 300 or 280 that scale is there. So, what it shows that some of the steels are more prone, or they are more sensitive. In HAZ normally you will see that you will have larger hardness, and at some places in some cases you have the hardness is not at all altered. It may be you can remotely connect with those concepts which we have studied, like when you have the carbon percentage is less, in those cases it is not hardenable. So, basically it is because of the martensitic or maybe benetic martensitic structure which you get. So, because of that what you get is you get this sharp rise in this range. So, most of the alloy steels they will be showing this martensitic or martensitic benetic structure over the wide interval of cooling, maybe from 500 to 800 to 500 degrees centigrade. Now, many a times we are also concerned about the hardness. So, if you talk about the maximum underbid hardness, so the maximum underbid hardness which is achieved So, the maximum underbid hardness which is expected for the non-structural alloy steels, so that is non-alloyed structural steels. So, they are basically calculated using certain standard formula, and that is given by Co, and he has suggested that this HV max, so Vickers hardness, that maximum value will be 90 plus 1050 C, and then you have 47 silicon, and further you have 75 manganese, and then you have 30 nickel and 31 chromium. So, this way these C, Si, Mn, Ni or Cr, normally they are in terms of percentages, and you can see that the maximum contribution comes from the percentage of carbon, and as you increase the carbon, so certainly that under the cooling normal cooling conditions, because the cooling rate is higher. So, in those cases you have hardenability is improved. So, that way its contribution is maximum. So, you are going to get even if suppose you are getting 0.1% of carbon. So, it will be you see that it will 214. If it has 0.2% of carbon, so it is going to 300, 0.3% of carbon. So, it will go to minimum of 400, and then you have the contribution by the different alloying elements. So, that way underbid zone hardness are calculated, and basically they are available also for the different steels or different plate thicknesses. You have standard formulas by which you can find the underbid hardness, and that value has to be limited. So, normally it is seen it is supposed that it should be maximum to certain value, maybe up to 350 or 400 Vickers hardness, because for low alloy steels because in the area of creep temperatures, so even it is stricter. So, accordingly for different requirements these so the value has to be that limit on these values are to be kept in mind, because that may lead to failure of the material under different conditions. Then so majority of steels will be showing that martensitic and martensitic benitic structures over a wide interval, that is from in the cooling from 800 to 500 degree centigrade. Now, the next property which is important to be kept in mind will be the toughness. So, toughness is a very important property for the material, because when you do the welding and your weld metal zone, in that zone you have the high temperature. So, that temperature is basically then the heat is dissipating towards the heat affected zone and towards the base metal zone. So, that leads to various phenomena, various microstructural changes. So, your change will be there also in the grain sizes, and that will induce basically that will be affecting the toughness of the material. Now, the toughness is normally affected because of the possible degeneration of plasticity, and that is in HAZ, which will be due to reason. One is that aging. So, aging that results into decrease in the toughness value below the A1 temperature, because you are heating and then further you are cool. So, you are while heating. So, below the A1 temperature it's like the aging effect. So, that that leads to the degeneration of plasticity in the HAZ zone. So, it's basically one of the reason is that, and another is that more conspicuous decline in toughness is observed, that is because of the grain coarsening in the underbid zone. So, in the underbid zone, as you know that there the grain coarsening is taking place, grain growth region is there. So, that is extended up to that region. So, because of that the grain coarsening is taking place, and because of that the toughness value is affected. So, the decrease in toughness value is also related to the formation of unfavorable macrostructure in the zone. So, basically you have the formation of unfavorable macrostructures, and that leads to the decrease in the toughness, and that is also known as the transformation embrittlement. So, basically you have the brittle embrittlement is because of the loss in the toughness. So, that comes into picture because of the decrease in the toughness value. So, if you try to look at the toughness value, if you do the experimental work has been done to measure the toughness value on the sample, and if the toughness is measured. So, how the toughness is varying on a welded specimen. So, suppose that you have a welded specimen. So, you have something like if you talk about a normal weld. So, it is going like this, and in that case you have the different zones. So, this is your weld metal zone, and then you have the different zones. On this side you have the heat affected zone, and then on this side you have the base metal zone. So, accordingly, so what has been seen that if you look at the different zones. So, this is your weld metal zone, and and then if you talk about this, so it has been done for the alloy steel. So, it is for the low alloy steel material. Now, at this stage your temperature will be somewhere close to 1200 degrees centigrade. Then further if you go, you have the temperature as suppose 900 degrees centigrade, then you have 750 degrees centigrade, and so it will go now further to 600 degrees centigrade, and then ultimately you have this as 400, and then you have 200 as the unchanged base material. So, if you try to look at the toughness values which are indicated by experiment in the different zones. So, what has been seen that if you come to this zone. So, at this point if you see at this point the toughness will be very small. So, it will be like this, it will be coming down, and that will be so in this case it will be smaller, and then the toughness will further increase, and then in this zone it will be further going this way. So, that will be the variation of toughness in the mild steel. So, basically you have the zones going like this. Zone will be your weld metal zone, and this zone is the overheated zone basically. And then the zone on this side where the toughness is again further decreasing. So, this zone is basically the possible embrittled zone. So, that is zone of possible embrittlement. So, there is a decrease in the toughness. If you look into this zone here, as the grain coarsening is taking place, so that there will be decrease in the toughness value. This is your on this side you have the notch toughness. So, so accordingly you have the and after that it comes to a constant value. If you talk about the high strength low alloy steels, where you have that is HSLA, where you have the grain refinement going on. So, in those cases the increase in toughness is there towards this side. So, here you have the constant value, but in this case your toughness is going on increasing in this region. So, that is for the high strength low alloy steels. Now, that basically will be depending. So, this change in the toughness, it is basically these values are affected by many factors, and these factors are basically by the chemical composition, then microstructure and grain size. So, these are the factors basically which are helpful in predicting these toughness values. They are affecting the toughness value, whereas the prediction of the toughness in the underbid zone is rather difficult. It's not easy to predict that toughness in that underbid zone. Now, the other aspect of this toughness of HAZ. Now there are other properties also, not about the toughness. Basically, it is about the other effect on other properties, that is your stress corrosion cracking. So, that also very much takes place in structural steels in the presence of certain sulfur compounds, like you have H2S or chlorides and alkalis. If the hardness of the underbid zone is very very high. So, that is normally you have what has been seen, that normally in the offshore constructions many a times you need to have you have to compel, there is a compelling on the designer to lower the carbon content, because the hardness which is permitted, it is normally smaller. So, if you increase the hardness, that is going to affect the properties of the materials that may fail. So, basically many a times in the pipes, offshore pipes or so, we try to limit the hardness to maybe the value of 150 to 200 maybe HB, especially when if they are under the subjected to the shore conditions. So, because you have sulfur and all that present there. So, in those cases we try to limit the hardness to maybe 150 to even the 200 or 250 maximum, the weaker hardness. So, that stress corrosion cracking is the another point which is very much to be kept into mind when we talk about the properties of the HAZ. So, that is about the effect, and in a nutshell what we need to know, that normally whenever we do the welding. So, as the structure microstructure is changed, so that leads to change in the properties of the material, change in the because of the change in the microstructure, as we have understood the different mechanism. We have studied about the different type of heat treatment processes also, and there also we have seen that I mean we can always correlate with the type of thermal treatment the material is subjected to. We can further say that this kind of microstructural changes is going to be be there in the material because of the thermal treatment. So, as we know that when you have the annealing treatment, in that case you will have the softening, which is softening is achieved, and if you have the higher cooling, in that case you have the hardening achieved. So, that way it will make the hard phases. So, that way then we also studied about different processes like for non-ferrous we had studied about, while we discussing about the heat treatment processes, about the heat non-press materials especially, we talked about the solution treatment, and then we talked about the aging process. So, that we know that we have the supersaturated solution, and then it is cooled, and then when it is heated further, so in that precipitates grow. So, that way you get basically the formation of precipitates which impede the motion of the dislocation in the journey of the movement of the dislocation to create the fracture or the deformation. So, many of the so, and if you try to leave that, if you do the if you do not do the artificial aging, so you can go for the even natural aging. So, natural aging also is there, and normally you have certain materials which are in natural way they age. So, there are aluminum 4.5% copper or 4% copper, that is duralumin. So, that is a natural aging material. But even the steels also, they are also susceptible to aging. So, normally the mild steel is very much susceptible to the aging, because if the nitrogen is present in the steel, in that case the precipitation of iron nitride is occurring. So, in that case these precipitates they will be precipitated at temperature below A1. So, when we are heating and we go to temperature below A1, in that case you have the precipitation of iron nitrides, that is Fe16N2, that is formed at even room temperature, and that is known as steel aging. So, when we try to heat in the range of 200 to 300 even, so in that band if you look at go towards the lower temperature side. So, in that region you can have the formation of these nitrides, and these are the precipitation. So, that is natural aging taking place. So, these are affecting the properties of the material, and these are the obvious effects on the properties of the material, because they are going to affect your microstructure, they are going to affect the mechanical properties of the welded joint. So, we will have discussion about other effects in our coming lectures. Thank you very much.